You'll just be on your own for keeping current during the summer, and hopefully the series will continue again in the fall. But today, we've got two students who have some connection with me. Namely, our first, Burkett, has been working on a master's project with me. And later, we have someone who's in the CPE, Stanford anyway. Computer engineering, thank you, program. One of our PhD students in that program, of which I'm the DGS. So we'll see something about computer engineering so shortly. But for now, we will try to wrap our brains around quantum computing.
Everyone hear me? Yes. So my master's project, I've been making a compiler. So I've titled the language QuantC. It's based on C, and as the title suggests, it's a CUDA-inspired language for quantum computing. So that. Trying to real quick, under 5 minutes, crash course on quantum computing. Qubits, which is the base unit of information in a quantum computer, they act like bits, but obviously, as the name suggests, they're based on some quantum phenomenon, a binary set of states, whenever they're measured. There's a couple examples of it. I'm not sure if anyone will be familiar with this, just like electron spin or anything like that. So basically, phenomenon, binary, just like regular bits. Connected, they can store a 0 and 1 just like a regular bit. They can also be in a superposition. Essentially a state where, when you measure it, the value you get when you measure is probabilistically either 0 or 1. Measuring a qubit, as I said, causes it to collapse into that 0 or 1 state afterwards. So measurement, looking at a value, unlike a regular computer, actually affects the state of the qubits. And a common representation of sort of the computations on qubits is as a circuit, with the operations represented as like quantum logic gates, similar to just classical logic gates, like AND and OR. Quantum circuits are just as computationally powerful as classical circuits. There's an analog to the AND gate, the XOR gate in quantum circuits, but there's other gates as well, which I'll show some examples of here in a second, that are purely in like quantum computing. There isn't a classical analog to them. However, quantum circuits do have some other restrictions placed on them, which classical circuits don't have. Gates and the circuits as a whole must be reversible. So at minimum, that means that the number of outputs, has to equal the number of inputs in terms of like bits, qubits. Gates can be used and gates cannot be used to arbitrarily copy or delete any kind of qubit value. Obviously, if the qubit's 0 or 1, then yes, you can obviously do that, much like a regular bit. But in any arbitrary state, no, you can't do that. Let's see, and just to, oh dear, for some reason, the equations decided to not show up, even though it does show up online. The value, so sort of the mechanics, again, very briefly. The value of a qubit, what state it's in, can be represented as like a normalized vector in the, as a two-element vector with complex numbers. There's some rules and reasons behind the things behind it, but the first coefficient is real. So what that means is that ultimately you can represent the state pictorially as this sort of diagram here called a block sphere. With the idea that the base states, 0 to 1, they're basically along this z-axis right here. Obviously the top is 0, you get the negatives, 1. And the idea is that all these quantum operations can essentially be thought of as just essentially taking an array in this sphere, just kind of rotating it around the axis. Gates themselves, as I alluded to, they're matrices, particularly unitary ones, which essentially is just for the complex matrices. It's just essentially the transpose is its inverse. And that kind of reflects the idea of reversibility. And like I said, measurements correspond, it's a little bit trickier mathematically to represent it, but measurements correspond to essentially randomly picking one of the base things, 0 or 1, the probability of it being dependent on the coefficient of that in the actual state vector. show up there. That's the generalized formula. It's not too important for this talk to necessarily know all the mathematics behind it, but just as like a brief overview of it. Like I said, here's examples of some of these gates. There's classical equivalence. Not is also equivalent in quantum. XOR, which is essentially just a controlled not, essentially just turning off this qubit right here, 0 to 1, based on this one, 0 to 1.
So we read it from left to right.
Yes, that is correct.
Okay.
And also there is the analog and. Also, as I said, keep in mind, these have to be reversible. So again, the number of inputs equals the number of outputs for all these gates. And then finally, we have an equivalent to the AND gate here. If you leave this last qubit right here, 0, whatever values these two are, again, as like the base state 0 and 1, they'll remain unchanged here, but the output will be effectively AND for this qubit. But as I said, there's also some gates that don't have an equivalent. There's the Hadamard gate, which essentially puts it into a 50-50 state. I go back to the diagram here. It essentially takes 0 right here along the z-axis and just rotates it, essentially this x-axis right here. Which, as I said, if you measure it, it's basically right halfway between the two. So either be 0 or 1 randomly, you can actually measure it. And
so going back to the AND gate here, aren't you destroying the lowest left input because it changes on the way out?
So the key thing with reversibility is essentially you have to be able to reconstruct, given the information at the input, back to the original. So for example here, what will effectively happen is, let's say this is some value of either call it A, it could be 0 or 1. B, again, 0 or 1. And this is just 0 here. The output will be essentially these two unchanged, and the result of the AND there.
I see. So you give it a non-quantum 0 as the third input.
Yes, you can give it put it in the zeros. That'll effectively be an AND. And likewise, if you run this, essentially run it backwards through this, go the other way. That's enough information to get back to the original A, B, where it's just 0. And like I said, the last page is a nice little thing. And I'm not going to mention too much of this. There is also a square root of NOT gate, which is, as the name sort of suggests, if you apply it twice, it's the same as doing the regular NOT here, which again does not have a classical handle. But like I said, it's a consequence of the fact that there's so many more possible states the qubit can be in. So just some simple examples here. This circuit, just a Hadamard in that controlled NOT gate. This results in a phenomenon called the entanglement. Essentially, if these are 2, 0 right here, for example, it'll map it to this state, or effectively what this means is, with sort of a 50% probability, you either measure both 0 or both 1. The interesting implication of this state, though, is the fact that even just measuring one of the qubits here, say Q0 at the end, will automatically make Q1 collapse down into the corresponding value as well. Because, kind of as the name suggests, the idea of measurement, you basically take a one state based on what you measure. If the output becomes 0, there's no other possible state it can be in other than also 0. And likewise for 1 as well. And just kind of to demonstrate this sort of classical equivalence, this is actually a full adder circuit as well. You can kind of tell, if you remember, that this is like an AND and this is an XOR. You can see these are like 2.5 adders at the end, with this last bit just making sure that after all this, the final outputs are back to A and B as before. This last one's not necessary, but if you want to preserve the values here, that's what this gate does. Okay, so with that, I actually get to the project itself. Sort of my design goals here is that I sort of create a language with syntax incorporating programs for both classical and quantum components. And I also want to minimize the overhead for learning the language. So I ended up, the goal is to extend an existing language rather than just create a new one from scratch. In this case, I chose C. It's also important to make a distinguish between the two, make distinguishing the two parts of code as clear as possible, so people obviously using it can clearly tell, like, oh, this is the quantum bit. You know, I need to have these expectations for what happens versus the normal code. And obviously only introduce new syntax for new concepts, try not to overload the meaning of existing symbols and operations, etc., to minimize confusion. Also, in general, also to abstract the communication between the classical and quantum computers. So this is one sort of cohesive, one big program, and there's not much to distinguish between what's no explicit requirement for you to have to figure out, okay, how do I send this code over there? It's all handled by the compiler itself. So this is some sample CUDA code, to show you what it's based on. You kind of see this classical C code here. This is just, like I said, it's taking some values, looping, going through a big loop through potentially a lot of them, and basically just assigning y equals ax. Of course, I just call this over there. For here, some of the important things to notice is some of the differences between this and the classical code. There's this global sort of keyword here, which is effectively just saying, hey, this is a function with code that's supposed to be run on a GPU. There's additionally some additional syntax which doesn't explicitly appear anywhere, but is just accessible only inside that function body. There's some additional code outside to just sort of allocate memory. I ended up not necessarily needing that, but that's an option as well. And of course, actually calling the code, or actually running it, looks identical more or less to calling a normal function like over here. This needs to be some additional syntax. So, like I said, I took that same idea as well. I added a sort of quantum keyword in there. Let's see. It takes the place of like extern or static, same sort of role. And the idea is that, obviously as it suggests, it's actually distinguish that, oh, this is a quantum function, this is running on the quantum computer. And likewise, you can also prepend, I guess, that keyword in front of variable declarations to say these are not classical bits, these are actually qubits. And actually calling the quantum functions, you can call it just like a normal function would. But what happens is, what the compiler does is effectively does something similar to this. It doesn't directly translate it into C. This is the effect of the effect if you essentially compile it back, sort of reverse compile it back into C, what it would kind of look like. So the idea is that the intermediate representation, like what my compiler ultimately generates before it ends up sitting off to the actual quantum computer itself, the handle is going to be stored as effectively a string here inside the code itself. And then instead of obviously not calling the function directly, because there is no function in the final product, instead it calls this helper function that sort of handles just saying, give me the string and potentially any other arguments that might need to be given for that code. I'll handle the steps of actually getting it to the quantum computer itself. And like I said, it's also assumed that whatever format I take, if there needs to be additional translations, because what I'm using isn't necessarily directly what a quantum computer might do in terms of machine instructions. You know, it might like lasers involved or something. So I'm not translating directly to that level, but instead sort of, like I said, an intermediary that assumedly the quantum computer will be able to translate into the real quantum instructions if necessary. And like I said, but there's also some constraints on these functions as well. Obviously, you can have quantum arguments. I think. Yeah, actually, I think I'm going to do that. So the quantum arguments, they essentially may be passed by reference. There's a bit of a debate with myself currently if I wanted to like make it a pointer or actually add like the ampersand, kind of like how C++ handles pass by reference. But the idea is essentially that whenever you pass these values by reference, essentially you're not passing in like a copy of the values. You obviously, as I said, you can't arbitrarily copy the values. You're instead essentially passing effectively a sort of address saying, hey, here are the qubits I want you to operate on. Work on these.
Right, but you can't do things like pointer arithmetic or anything.
No, pointer arithmetic is disallowed.
I think you'd be much better off doing the ampersand.
That's a quick fix. So they must have by reference. Only functions with exclusively classical arguments passed by value can be called from classical code. Again, disallowing vector values, at least in the definition of the functions, as well as obviously you can't really pass in a quantum value for classical codes.
Just a point of clarification, looking at the first example of the third section, quantum void. It's not returning a quantum void. That's a quantum function returning a void.
Right.
So far, all of these quantum functions return classical results.
Yes, and I think that's actually, yeah. They can recognize their only classical values, correct. Yeah, and I think it's mostly just the fact that how the syntax works. It's in the same sort of class of keywords as static and external, which typically are on the end, I believe. I have to double check and see if C grammar actually allows you to switch the order of those. But yeah, that's mostly just because of the convention from those again. Static, external, etc. Those kinds of keywords typically go first. And often not allowing recursive calls to other quantum functions. So you may certainly be allowed to call another function, like another quantum function from another quantum function, but you can't recursively call itself. Let's see, yeah, that's the semantics. Obviously, with these being qubits, there's, as I mentioned before, there's restrictions, especially since we're going to define these as variables as well. So the idea is that between two quantum variables, the assignment essentially has moved semantics rather than copy semantics. Sort of, in a sense, the variable on the left-hand side has to be uninitialized, and any variables being used, again, these are quantum values, on the right-hand side, they can't be used again after that expression. And obviously, they can be used multiple times in the same expression as well. And obviously, we're working on more complicated expressions, like, for example, this last one here, where it's sort of binary operation, but of course, you can potentially think of these as being potentially many array expressions at the end. Establishing a sort of syntax to say a one-to-one mapping of like only effectively. And so for this example here, the idea is essentially basically left to right would be the individual. So this operation, which I'll go into detail more in a second, after this operation, Q2 will effectively be whatever the qubits of Q0 and Q3 will be the qubits of Q3. So essentially a remake. And like I said, all this will be checked by the compiler at compile time. If anyone's ever programmed with Rust, I think it does something kind of similar to that, in that sort of by default, once it takes an expression or you give it some value, like a Rust function, it will kind of say like, oh, this has been moved. You can't call it again afterwards. So if you've had some working with Rust before, you might. Semantics is roughly similar. But onto the other values, obviously classical works fine. If you're going from classical to quantum, that is essentially just saying initialize the qubits to the base states of that classical value. And obviously you can't assign quantum to a classical value without first measuring it.
When you declare A and B as int, you mean just bit?
Yeah, without the quantum keyword, the idea is by default. These are the classical bits.
Okay, so an int is not 32-bit integer, it's
Well, what it's really dependent on the definition of the quantum computer itself. It could be 32, but obviously with some physical limitations of quantum computation currently, both simulation and physical. It's like at the end much smaller, maybe like a byte or.
Okay, so
right now you only have 5 bit.
Yeah, so maybe it's a,
5 bits would be about it.
so we understand in line 8 to say, take this 5-bit integer A and assign it into a 5-bit quantum integer, or 5-qubit.
Yes.
Okay, I understand.
And so just kind of quickly going over some of the syntax here. For these classical gates, I did decide that, kind of mapping it closely related to binary operations, bitwise operations, I should say, make the most sense. They're relatively close enough. So not implicitly C naught, like the effect is effectively XOR. And again, because of the folly gate, as well as I showed before, it has 3 inputs. So I decided to actually add it as a ternary operator as well, kind of saying, oh, here's the two values, once you add together, essentially put it in your results. The result qubit. And likewise for, the construction is very similar. It's a default gate, sort of, not gates before and after the controls. Kind of to Morgan's law in a way. So just as a shortcut, say, yes, you can also order them. And it works.
And this is prerequisite that Q1 and Q2 be defined and the result not be defined. And afterwards, Q1 and Q2 are still defined.
Yes. Well, after this expression, Q1 and Q2 would be no longer usable.
Oh, okay, no longer usable.
Again, that's to avoid like, potentially doubling referencing qubits. You can't particularly do operations to themselves. You should control the other qubits.
Control it just got through the whole thing. So you could reuse it.
And yeah, that also boils down to some issues with semantic checking. One option is I could check for each one to say, does this operation preserve it? Or the other option just saying, hey, all these values are invalid, give them a new name at this point. Because there's a couple options there. I ended up deciding to stick with this one. The one I talked about earlier, where essentially, once you use an expression, you have to give it a new name.
So isn't the use of that swirling the problem? Because it's perfectly legal to write something like A excludes the word B semicolon. That means compute the exclusive of A and B and then throw away the result.
I'll have to look into that a bit more. I wasn't aware that was a particular thing you could do.
Yeah, basically C doesn't have a sign. It has expressions.
Right.
You can make an expression into a thing with a semicolon.
Right. Okay. So yeah, I'll double check. I have to double check that semantics. That should be.
Kind of an issue for all of them.
Yeah. Like I said, at this point in my sort of progress, which I'll get into, there's definitely a lot of still potential edge cases in how this works. I'll need to test out.
Yeah, well, at some level, I'm not too worried about this because the types of the things that you're putting together have to be in one place, right? So even if the syntax is the same, the semantics are different, so it should be okay.
Yeah, that's definitely something to consider too. Again, trying to minimize, keeping it as sort of consistent as possible semantically. So yeah, obviously on operations, there's unary. There's a whole different bunch here. I decided that for sort of purposes' sake, basically to have the operation be the percent sign followed by sort of the name of it. Some of these obviously are just the values here. There's a Hadamard as before. Some of these are parameterized. You can give it, generally you just give it some sort of float value representing like an angle. And it will, it's more generalized gate, you can do that. Or some of these are like just a fixed version where like they say that value is a fixed value. Any questions?
So these expressions then you can assign the result, or are these modified in place?
The idea is that these sort of expressions, like even nest things as well, like a normal expression. The idea is that, again, they kind of even move semantics. The value of the expression would be essentially the qubits themselves, like what qubits are, say, 0.
Well, go back to the example of Hadamard. Hadamard at Q1. Do you say that by itself and that modifies?
Yeah, oh yes, I see, yeah.
So is it in place modification, or then you have to assign the result to something?
The modification is in place. So the idea is that you could just say Hadamard Q1 as just a statement in and of itself, not needing to assign it. And then in that case, yes, you could still use it. It wouldn't be reassigned at that point, so you could still use it. Also, there's some binaries. In these cases, these are all basically forms of swapping. So swapping is allowed with qubits. That is a unitary matrix, so that is a gate you can use. And like that is using syntax for locating brackets. And also, there's some simple modifiers to add because the intermediate representation I'm using does make it relatively easy to say, oh, here's a gate, add some modifications to it as well. One of those is being able to add control qubits as well. So obviously, C not related, but it is literally just a not gate that you add a control bit to it. So you can do that with any arbitrary like unitary gate as well. Just say, hey, Take the header mark, for example, now add a controller to Q2 and apply it. And I believe you can extend that out basically as many times as you want, theoretically. And likewise, there's sort of the inverse of A here, because, as I said, they're unitary matrices, mathematically speaking. So there's always an inverse, which is at variance of the transpose of it. So these inverses always exist for these gates, so you just have the syntax saying, basically negate the gate value itself, and then effectively, like in this example here, basically just be the same as 2, basically. Yeah, as for the implementation itself, so going through the phases of the compiler real quick. For the preprocessor and linking sort of both ends of the stage, there really wasn't much change in there itself, so I decided to basically just invoke GCC to say, hey, preprocess this for me, or link the final product. With the Lexer and parser parts, I used the Flex Bison. You've heard of Bison, it's essentially the same thing. To generate the part where ultimately I get to an abstract syntax tree, where I can actually then go generation. The AST and the semantics checking part, that's hand-coded by me in C++. I'm handling all that. And then once I get to code generation at that phase, I'm using sort of two parts. Obviously, I'm generating the classical code using this LLVM library. It just has a lot of features in it, so it makes generating classical code relatively easy. And then there's the harder part for the actual quantum code itself. That will be coded, as I said, as a string in there, but I'm using the Quill intermediate representation to translate that to those instructions. Yeah, in terms of progress, I've established a compilation of a minimal amount of classical quantum code. Basically, I can compile main and make a call to a quantum function. That's relatively simple, which I'll demo here in a second. I can actually compile down to genuine Linux object files and executables. So I'm not just generating the intermediary that we're down like an interpreter of sorts. I'm actually generating an actual code object. And I can, in fact, even link with the standard C library, so I can like print the signature from print F, and I can use print F just fine. Again, because I'm using GCC for the actual linking phase. So it automatically will just link that in as well. I've created, obviously, a basic version of the communication quantum code, and it's currently talking with a local simulator on my laptop, which is local HTTP testing right now. And sort of the next phase for my project is sort of complete code generation for all the quantum operations I showed before, handle assignment of quantum variables, consider what it needs, maybe, for example, see if all that checks out, make sure that's consistent. Obviously, handle generating code for multiple quantum functions, at least in the same file. There is a potential issue in figuring out like how do I link them across translation units, but I'll get to that bridge once I get there. And also adding all or most of the classical constructs like if else and for loops, which Quill interestingly does give you the ability to do that. They're exclusively controlled by classical values, but you can define essentially jumps and loops in Quill as well. And unless anyone has any questions, I can go ahead and do the demo real quick. Okay. So I'm available. I don't want to eat too much time. So this is the actual example here. So this is like a sample. We've got a very simple, very small program at this point. But obviously, one I've included the signature for printf, which is actually in the actual C library itself. And my quantum function here, hello quantum, I've defined essentially a Boolean value, set it to 0, which for Quill, they're automatically 0 by default, so that's basically anything. And then basically Hadamard, apply the Hadamard gate to that qubit, and then measure it and return it. And essentially just print out that value on the command line. So, switch over here. So let's see. Let's see. I believe we should be able to. Yeah, this is binary here. I've actually filed it referencing that. Real quick, just to show you what's actually doing stuff. The actual, I do have the generated intermediary code in case anyone wants to look at that. So as you can see, I do have like the string values here for the actual code itself. Essentially,
Is this Quill or is this
this whole file itself is Quill. The string right here is actually it's the whole file is albeit, intermediate IR itself, and the string here is actually the Quill code. So obviously this is just saying declare essentially a return register, apply how to mark 0, and then measure it, store it in that register. And then with the quantum communication code, it just assumes by default that the return value of the whole program is just in something called R0. And otherwise it's saying yes, but as a string, the simple defined function call. So if I run this real quick, right on doing a.out. Essentially what it does, this is effectively just a coin program at the moment. So, yeah, nothing too interesting at the moment, but it's like I said at the beginning of something really interesting. So, unless anyone has any questions, I think it's time for the next speaker.
Can I ask one? Great, thank you. So like whenever we had those gates up there, so the reason that complex analysis came about is because mathematicians were able to arrive at some solutions but not straightforward with other ways. So they knew that there was something missing in the algebraic structure. Some of those gates that you had up there, they almost seem like analogs to like the solution of x squared plus 1 equals 0, where like they had to change it. Like when you have the not, and the square root there.
Right,
the symbols seem kind of similar.
Yeah, definitely. Because I'll do this real quick because it's actually working. But yeah, all the matrices and vectors that go through the mechanics, they're all defined in complex numbers. So there are, like you said, like the solution to x squared plus 1 equals 0, I believe. Yeah, so obviously complex numbers get involved. So yeah, there is actually the possibility of having those intermediary states. And like I said, there's a lot of linear algebra involved with all these things as well. So I think there's like a few example algorithms I've seen that do things like try and determine the eigenvalues, trying to do computational values. So yeah, there's definitely quite a few applications in that.
Great. Well, I'm looking forward to seeing more complicated examples actually running.
Yes.
Very nice.